Okay, sorry, camera not working today. Um, but I'll just go ahead. I want to do something a bit different today. So I mean, not a bit different. Sorry, I just wanted to kind of take a breath for a second and sort of look around and other parts of the paper from multiverse computing. Because remember, we're kind of like we've kind of like gone through a bit of the D-Wave stuff. We've gone through a bit of the tensor network stuff, and now I wanted to go and do a bit of the variational stuff. And I'll come back to the other parts. I know I haven't finished all of them. It's just like I think I've gone deep enough to really uh, to kind of really understand sort of at an intuitive level what's going on. And I think then programming the rest will just be like a longer session that I might even just do live later. I don't know. We'll see. So I'm using that my camera. The fact that my camera is not working, I'm just going to go ahead and do this full screen. So we've done the tensor network. Now that looks not the first time I read that I was like, what the hell is this? But now I start kind of like see these, right? So we've done these, we've done these. I mean, I'm not gonna dive into the classical part, but I guess the Gecko solver is something you can just like use out of the box somewhere, right? Yeah, it's actually there's an optimization suite. Okay, so I'm dynamic optimization. Uh-huh. Okay, so I can just probably use that. Quick start model building. I mean, that will be just worth investigating as well. Um, equations, variable types, objectives, example, uh, tuning, global options, deep learning, chemical library examples. So is there like just a Cubo thing in here or no? I thought they'd have something specific to that. Otherwise, I don't know where to start even. I mean, have they done like the Gecko solver, the exhaustive solver? Or is exhaustive solver rather another thing? What does Gecko do? Real-time optimization, dynamic optimization. Mm-hmm. Objective functions, function. Gecko find ground state of Hamiltonian. No. Okay, so I might have to do some digging there as well. But what I'm interested today is in the Vqe, probably the Vqe constraint, trying to understand um, what they've done there. So where's this here? Vqe. So first they probably the variational quantum eigensolver is the hybrid quantum classical algorithm. That is the variational position of quantum state and the approximation to the ground state. I mean that's basically what we're going to be doing with the MRG, right? Just with the quantum circuit. So we're gonna probably have encode the Cubo as an Ising model and then use that as an ansatz for the VQE. That's my guess. The ansatz state is itself a real quantum state that is implemented on a quantum processor by some quantum circuit. The gates and the circuit depend on the parameters, which are variational parameters of the algorithm. After estimating the energy of the quantum state via sampling, the parameters are then fine-tuned to lower the energy using conjugate gradient or whatever. The performance of the key depends strongly on several aspects, but mostly important are the choice of variational quantum circuit. In some cases, the search for some complex ground states requires strongly entangling quantum circuit, in turn increasing the complexity of the algorithm. However, VQE is still a good option as an optimization tool for current noisy processors. For the sake of this paper, we implemented Vqe optimization in the quantum processor of an IBM Q up to 12 qubits. Moreover, in order to tackle slightly larger problems than those, reachable by plain vanilla VQE, we implemented a new and original approach. That's what I'm looking for. New and original approach, which we call VQE constrained. Okay, I'm curious now. So what is this new and original approach? Let's see. What is the timing? I don't have much time today. But, yeah, cool. So the idea is, okay, so the idea here is quite simple. Use VQE to sample several low energy states at every rebalancing time t, and then use a classical approach to find which combination of these provides the highest returns over the whole trading time period. Okay, so it's an actual, so it's not a modification on the circuit. It's just using VQE with subsets of qubits, and then which combination of these provides the highest returns over the whole trading time period. This approach is inspired by low-energy subspace methods in physics. It follows the intuition that the optimal portfolio can be built in most cases from a combination of near-optimal states. Thus, we identify these states as VQE. This is the computationally expensive part. And then recombine them and estimate their associated profits classically, which is computationally cheap. So in figure 2 we see a dendrogram showing possible data clusters. The Euclidean distance between the different time series is shown in the vertical axis. Okay, that's it. There's no more explanation. Okay. Next steps, more constraints, exact linear transaction costs, market impact. This study is damn, like, it's just really, I think it's really exhausting. It's really well done. It's really damn detailed. I mean, improve hardware and codes, acknowledgements, that's it. So it's really, as far as we know, is unique, yeah, but it's not really. How does this perform? So it is able to do up to the S size. Which is not a lot. Oh, M size, sorry. That's not bad. Okay, still something. VQE constrained. But the runtime, this is runtime and this is the Sharpie ratios, right? Table 2. Okay, that's the stuff in here. That's all they say. So, but there's no really hints into how they've actually done this. But we could try to reproduce, what I could try to do is try to reproduce these here, right? What is sample index? So let's read that again. So what they do is, to tackle slightly larger problems, we implement a new, because with VQE what you would do is you would just go and kind of have like the you have your Ising Hamiltonian, and I guess you can just do that. Ising times Hamiltonian, right? I mean, here I would even just say I'm not gonna actually program VQE, but we could just use Qiskit's implementation. What's Qiskit VQE? The observable. Trial state ansatz from macros variational forms in one of the classical optimizers. The ansatz is varied via its set of parameters, but the optimizer expression value of the measure Hamiltonian. Okay, no, so the Hamiltonian will be, yeah, so that will be basically the Ising Hamiltonian from the Q, like the Cuba translated to an Ising Hamiltonian. That's what we're going to do here. And so I wonder, can you see the mouse? I'm not so sure if you can see the mouse. Whatever. And then ansatz will just like, I don't know what a good ansatz would be though for these, to be honest. This is how the Hamiltonian may be written. Yeah, that was the original paper. I don't know what ansatz would be the best for these. Qiskit Vqe. So I guess you give it whatever ansatz you want in here, right? That's the idea. Just choose whatever you want. Yeah. So, okay, but let's not get distracted. So go back here. So Vqe constrained would be sample several low energy states at every rebalancing time t. So then use a classical approach to find which combination of these provides the highest returns over the whole trading time period. So how would you do that? So you would just have, so as a result of VQE, you would have a subset of things to invest in each trading step. And then what you want to do is you want to have which combination of those would give you the highest returns over the whole trading time period. And that is cheap computationally because how would we approach these problems? So this would be basically be so you have a set of like asset investments, like the percentages and whatnot, and so you would just calculate what's the optimal. I guess you would have to still consider what's the maximum amount of investment you can do, but like they don't expose a lot of the details in terms of how they do the constraining here. So do they for example say, hey, for all these like SAP runs of VQE, are we using a static, like are we always using the same type of like subset of, because I'm assuming what you're doing is they're just taking a subset of the assets. So they're just doing VQE to sample several low energy states everywhere. Exactly. They were rebalancing time. Then we use a classical approach to find. But like, I'm assuming they do these with, let's say if this is, how many, so like it's a portion of the size, right? It's a portion of. So what you're doing for size M is you're doing like, for example, right, like you're splitting these into smaller sizes, like sizes S, or you're finding solutions for several solutions for like smaller portfolios, and you find what combination of them. But that's still, you gotta fix that somehow. Otherwise, you also have an intractable problem, right? Because you have like many possible combinations that you can have. You could, I don't know, you could use just one portfolio. You could just use like 5 in step 1. Hmm. But we will definitely give it a try somehow. So, yeah, basically. So that's kind of basically it. Now the question is, do I want to implement that like from scratch, like Vqe, or do I want to use Qiskit's Vqe? I'm almost thinking like implementing it from scratch can be just a fun exercise as well. Like including stuff like the gradient descent and stuff like that. I'm not really. The thing is, I'm not gonna be able to get this in any way, like, super performant or whatnot. But we can take a look at. Then also how Qiskit does it. I mean, what do you need here? An operator, a parameterized circuit used as an ansatz, the optimizer type, and then the initial point. So the initial parameters for the expectation converter, and that's it, like a callback and blah blah blah. Yeah. Okay. I think we can implement Vqe by ourselves. That's probably going to be more interesting. And we want to run these on an IBM machine, so we're going to have to use Qiskit for these. Good. I mean, they even like fit assets after clustering from 50 down to 6. Horizontal axis is the period of time considered for this clustering, 2 years. So, what did they use the clustering for, though? Was it for Vqe, or was it like... The assets trend is shown here, group by cluster. So even dimensional reduction methods such as clustering serve the purpose of discarding relevant degrees of freedom early. We have observed that assets with which simultaneously present low variance and low returns tend to not be part of the optimal portfolio. Indeed, investing in these assets promises consistently low returns by discarding assets which simultaneously have sub-average variance and sub-average returns. Our dataset can be reduced from 52 down to 28 relevant assets. Prior to clustering, we may also eliminate the noise in the data by applying a Hodrick-Prescott smoothing, which extracts the data trend. We then compute the occluding distance in the data trend for each pair. This allows us to identify the degree of correlation between assets. I know this dendrogram is dendo. Correlation between assets. Okay, so that's nothing to do with the Vqe. It's Vqe is more. It's just for the correlation of between assets. This is for just data, kind of cleaning out the data and stuff like that. Preparation of the data. We'll consider the portfolio rebalancing to happen once monthly for the sake of concreteness. The returns between transactions are calculated as the sum of returns during the course of that month. Note that we would have calculated them on the basis of rolling average. This has the advantage of limiting daily fluctuations. Okay, so they really, so this is just the pre-processing. But haven't they used these for all the algorithms, or is it just like once we get the optimal portfolio trajectory for clustered effective assets, we unfold the investment by assuming an equal investment on each asset forming each specific cluster. Okay, cool, fine. Still Vqe. So where do we even start? I mean, I'm just gonna get the basics in like 10-15 more minutes, and that's it. Vqe. How do I implement gradient descent? It's how to implement gradient descent in Python. Let's see. Gradient descent in Python. Initialize parameters. Run a loop to perform gradient descent. So what is a loop doing? df. So what is df doing? That sounds like the derivative. Gradient of our function. Ah, so you actually pre-calculate the derivative. Is that really how you do it? How do these general algorithms do it? I mean, you're giving them a function. How do they actually calculate the derivative of these? What am I doing? So, workspace, portfolio optimization. Actually, I didn't commit my NPS stuff. Git add, git commit, NPS stuff, git push. Cool. So how do you? What I want to actually have basically Jupyter notebook. So how do you implement gradient descent? That's the question. Okay, so I'm gonna make a new notebook, and we'll call it Vqe constraint. NumPy, import NumPy as NP. How do we do this? So let's implement, like, how do we implement gradient descent from scratch? That's I don't like that because they just like they do that manually. Like, that's not what I want to know. Python and NumPy. So gradient. So my setup from the above code is, but it should be, oh come on, that's a shitty way to ask a question. Python programming. The forward and backward pass. So input forward pass, sigmoid, forward pass, chain rule, Python implementation. How do you, so we can start calculating the gradient of the error relative to the weight as given in the next figure. Using the equation below for calculating the gradient might be complex, especially when more inputs and weights exist. As an alternative, we can use the chain rule which simulates the calculations. But it's again like, it's just again like by hand. I just want to know how does a general optimizer do these. Percent generally in Python. That's probably the bad way to ask, but yeah. Gradient descent implementation from scratch. Gradient descent. Again, they use the cost function, and then you pre-calculate the derivative. Is that it? Like, because my cost function is gonna be, what is it gonna be? So it's gonna be the energy, right? Maybe. How to implement gradient descent on a quantum circuit? But there's the paper where they talk about like a more efficient way of doing that, right? Vanilla gradient descent, quantum natural gradient descent. But maybe I could do that. Maybe I could just do that. Yeah, maybe. So let's just fly through these. The most successful class of quantum algorithms, blah blah. Vqe, the natural gradient. So in standard gradient descent, each optimization step is given by where this fancy thing is a cost as a function of the parameter theta, and this is the learning rate or step size. In essence, each optimization step calculates the steepest descent direction around the local value theta t in the parameter space and updates these by this vector. The problem with the above approach is that each optimization step is strongly connected to Euclidean geometry on the parameter space. The parameterization is not unique, and different parameterizations can distort distances within the optimization landscape. For example, consider the following cost function L parameterizes in two different coordinate systems. Okay. So that depending on how you're framing the coordinate systems, you're going to have different. Yeah, that's like more a smoother way down to the minimum, and that's a bit more like you're not really getting there. Performing gradient descent on the theta 0, theta 1 parameter space, we're updating each parameter by the same Euclidean distance and not taking into account the fact that the cost function might vary at a different rate with respect to each parameter. Instead, if we perform a change of coordinate system, reparameterization of the cost function, we might find a parameter space where variations are similar across different parameters. This is the case with the new parameterization. The cost function is unchanged, but we now have a nicer geometry in which to perform gradient descent and a more informative step size. This leads to faster convergence and can help avoid optimization becoming stuck in local minima. For more in-depth explanation, including why the parameter space might not be represented by a Euclidean space, that's an interesting idea. However, what if we avoid gradient descent in the parameter space altogether? If we instead consider the optimization problem as a probability distribution of possible output values given an input, a better approach is to perform the gradient descent in the distribution space, which is dimensionless and invariant with respect to parameterization. I'm not so sure I grasp that. As a result, each optimization step will always choose the optimum step size for every parameter regardless of the parameterization. In classical neural networks, the above process is known as natural gradient descent and was first introduced by Amari. The standard gradient descent is modified as follows, where F is the Vqe information matrix. The Vqe information matrix acts as a metric tensor, transforming the steepest descent in the Euclidean parameter space to the steepest descent in the distribution space. What is this? God. The quantum analog. In a similar vein, it has been shown that some sort of inverse. Block diagonal metric tensor. Okay, so the idea is that because this is a matrix, you probably can implement it in a quantum computer. You can approximate that, and so that's it. That's interesting. And so this means though that you get the initial state, the layers of non-parameterized gates, layers of parameterized gates. It's the generator of the parameterized operation. I don't know what the generator is. For each parametric layer L in the variational quantum circuit, the NL and NL times NL block diagonal sum matrix of the Fubini static tensor is calculated by So are those blocks basically the non-parameterized blocks actually already doing the optimization? Or so create subcircuits consist of all the gates prior to the layer and observables so the generators of the gates in the layer. What are generators? In math. It's a generating set that has a simpler set of properties than the generating set. Okay. The block diagonal matrix must be real and symmetric by definition. We can repeat the above process to compute G1. The sum matrix G1. Interesting. While the off-diagonal terms require covariance between the two observables to be computed, putting this all together, the block diagonal precision is this. Okay. So basically, you run all these things to calculate the different components of this matrix, which what is going to do is going to actually, what is it going to do? So the space of quantum states instead possesses a unique invariant metric tensor known as the Fubini study metric tensor, which can be used to construct a quantum analog to natural gradient descent. What is these? It's again on projective Hilbert space that is a complex blah blah blah. A Hermitian form defines an inner group, subgroup. That's too complicated. Pronunciation. Let's assume that studies. Since it's actually a German name, the correct way to pronounce the U in studies, like the U in Fubini, in terms of Studi. Yeah. Okay, but I don't know exactly what it is. So, yeah. The space of quantum states instead possesses a unique invariant metric tensor known as the Fubini-Studi metric tensor, which can be used to construct a quantum analog to quantum gradient descent. The space of quantum states. Okay, so I think what this means is basically there's this matrix which somehow it's going to guide you through the gradient. This matrix depends on the way your quantum circuit is going to spin out a quantum state space, which is you have your ansatz, and then you know that that's going to kind of that's generating a space of probability distributions, and that's going to depend, of course, on the parameters of the circuit. But what you're doing is you're somehow calculating this matrix by running these different things in here, which we'll definitely try to understand. And then you're using this matrix to you're calculating it for each iteration. So you're actually probably calculating it for each amount of and this matrix is going to tell you what's the next parameter that you're going to have, and then you're going to kind of compute the next new circuit, and you're going to recalculate the whole matrix again, probably. So now you have the matrix. As opposed to our manual computation, which requires 6 different quantum relations, the penny-lane Fubini Studi metric tensor implementation requires only 2 quantum relations, 1 per layer. This is done by automatically detecting the layer structure, noting that every observable that must be measured commutes, allowing for simultaneous measurement. Therefore, by combining the quantum natural gradient optimizer with the analytic parameter shift rule to optimize the variational circuit with d parameters and blah blah blah. Non-metric tensor method supports computing the diagonal approximation of the metric tensor. So quantum natural gradient optimization. Okay, but it's not like, because I had a misconception before. I thought it was something that you're calculating somehow the descent within the circuit. What you're doing is you're calculating this matrix that tells you that it's somewhat like a better measure of distance, kind of like it's representing the geometry of the space better than just like using the Euclidean distance, which is essentially what you're doing with the classical gradient descent. Interesting. But still, how do you calculate gradient descent? Like, that's something I'd definitely like to know. Just for my own curiosity, I guess. So, one last try. How gradient descent. Yeah, how do you do this on a quantum circuit actually? Because you have a circuit, you have a list of parameters, and that tells you these. It's like it almost feels like you'd actually have to do small trials and kind of really find where there's the steepest descent. Like, you know what I mean? But that would be stupid. Because with you don't have a function. Okay, but you have a matrix, which is the sort of the circuit unitary kind of thing, and that transformation is your matrix. Maybe that's the way you do it. You know what I mean? That you have your circuit kind of is equivalent to an actual matrix, and then you unitary matrix. Yeah, but that's pointless because for big circuits, then that's not the way to do it. You don't have a function. You have just a set of parameters. I mean, I think it seems like that should be just trivial. Because everywhere is just you calculate the derivative by hand because that's your cost function. But yeah, that's basically you know these. But how do you do these on a quantum circuit? I mean, like, can we check Qiskit's code for these? Like, this is Vqe, and you give it like an optimizer. Optimizer. Are you kidding? Optimizers. Conjugate gradient optimizer. What's the Vqe Optimizer? No, that's just these. Okay, it's just the it's just the yeah. It's not what I wanted. So they actually don't have it. They have the conjugate gradient optimizer. Atom. CG is an algorithm for the numerical solution of systems of linear equations whose matrices are symmetric and positive definite. It is an iterative algorithm and is used as an initial guess to generate a sequence of improving approximate solutions for a problem in which the approximation is derived from previous ones. Okay. Pounds required. So probably. Okay. SciPy optimizer. So it's just using the Psi. Okay, so this is just using the SciPy optimizer. Okay. I don't know. I really wanna. I really wanna understand how you calculate the gradient on a circuit when you actually don't know the function, right? Like okay, you know for small circuits, but you don't know for like big circuits, right? Because you cannot like compute the matrix, the unit rays, just too big. If you have like 20 qubits or something. Um, maybe it's not too big because for 2 qubits is for no, it's too big actually. It's definitely too big. It grows exponentially actually with the amount of qubits. So how would you do that? I don't know. Anyway, well, next video.